So integration by substitution, we're going to be doing the same integration patterns that we just learned in the last class. The only thing that's a little different here is these are going to look a bit more complicated, as in, you know how we don't have an integration pattern for something like the product rule or the quotient rule that we use when we differentiate. If I need to integrate something and it looks like there's something that is being multiplied that I can't just multiply out, or something that has a division problem in it, but I can't simplify it very easily, then I sort of need a tool that's going to help me put this in a form that will be more manageable to work with. So what we do is called integration by substitution, and it simply lets us kind of not get distracted by all the extra stuff and see how to make this work. So let me just kind of show you how this is going to be useful. For instance, we know a rule that says if we are trying to integrate some function and there is an exponent on it, then we know the integration pattern says we could raise that exponent, add 1 to it, raise it to the next highest power, and divide by that new exponent, right? That's what we just did in 13.1. If we had x squared and we wanted to integrate it, it became what? X to the third, but then we divided it by that new exponent. So we divided it by 3. So really, this is the rule we just covered. Now, what we're going to do today is we're going to see maybe instead of it just being an x squared, maybe there's a bunch of other stuff with it. And so if we just change the other stuff, like maybe it's a parentheses raised to a power, we might be able to replace that parentheses with u, okay? In other words, we're just going to say, instead of getting worried about all this other stuff, let's call that u. And as long as we can differentiate whatever u is and get a replacement for our, instead, because it won't be a dx now, we're going to have to differentiate with respect to u. That's going to give us a tool to use this rule we just learned when things get a little more complicated. It'll work if it's e raised to some power, but now the exponent is more than just x. Maybe it's a function with x in it. We could replace that exponent with a u, and as long as we can differentiate it and come up with a du, we will be good. And the same thing with our natural log. If we had 1 over x, we know that it integrates as the natural log of x, but maybe our denominator won't just be x, it'll be something with x in it. So let me just kind of walk you through some examples here, but I do need to give you a couple of definitions before we get started. Okay? We have to be sure, first of all, that we're working with a function that is differentiable, okay? In other words, it's got to be something that it's possible to take the derivative of. Then what we would know is that we can take the differential dy of the dependent variable y, and that becomes the product of f prime of x and whatever the dx is. In other words, dy is whatever that derivative is times dx, okay? That's what let us end up with something that we are going to be able to integrate. It had to be something that was differentiable to begin with, okay? And when we recognize that we've got something to try to integrate, here's how substitution works. You're going to choose one part of the integrand to be your u, okay? So in general, if I've got two things being multiplied together, I'm going to look for the one that probably has the largest power on one of the variables. whatever would have the largest power is most likely going to be my U. And I'm going to hope if I find the DU for whatever I decided U was, it's going to give me the other pieces that are there that I wouldn't have known what to do with otherwise. When we look at an example, I think that will make more sense, okay? So what we've got to make sure we do, if we're going to replace part of this thing with U, we got to get rid of everything that has an X in it, okay? So we'd have to be able to change everything to something in terms of U and DU. Otherwise, I'm not going to be able to integrate it, okay? And then we will eventually talk about how you would evaluate. I'm not sure why this says this part here, because we haven't talked about how to evaluate definite integrals, but we will be doing that next class. So here's the idea, okay? We are going to find each indefinite integral and check the result by differentiating. That's the beauty of this. We can still take our answer, differentiate it to make sure we get back what we started with. Now, do you recognize why this is not easy to integrate the way that it's written? Exactly. I've got three terms, a trinomial raised to the third power, and then there's this other parentheses here that's being multiplied by it. If I wanted to distribute through so that I would get rid of all the parentheses and I could integrate term by term, I would have to multiply this guy together 3 times and get some big monstrous polynomial and then take everything in that polynomial times 6x plus 7 before I could do it. Now, that's doable. Does that sound fun? No, that sounds like a very long and tedious process. So here's how integration by substitution would work. If I compare what's in this parentheses and what's in this parentheses, which one has the largest exponent? The first one, the one that's 3x squared plus 7x minus 2. So when I realize this is not easy to integrate like it is, let's take the parentheses that have the biggest exponent, and we're going to let that be U. So if U is 3x squared plus 7x minus 2, okay, remember, I've got to replace everything here in terms of U and DU. So I need to differentiate what this U is and see if it gives me what I need for my DU. So how do you differentiate 3x squared? That becomes 6x plus 7. And then, of course, the minus 2 becomes a 0. So my DU would be 6x plus 7. Now, let's look at what we have. If all of this becomes U, that's U to the third power, right? Do I have everything I need for my DU? Because remember what I did, if I'm differentiating, my DU is going to be whatever this is with respect to X. Do I have all of this kind of floating around out here that was my problem, why I couldn't integrate originally the way that it was? This is DU. I've got replacements for everything. So what that means is I could now integrate by just writing this as U to the third DU. Does that make sense? I just changed the X's to something else that was easier to work with.
How would you like to explain it?
Yeah, it's a mindset of trying to figure out, if I look at it and I go, wait a minute, I got a problem, I can't integrate this like it is. We want to see if we can come up with a replacement so that the integration is easier. Do you guys remember how to do synthetic division? You know what polynomial long division is? In some respects, that's kind of the concept behind synthetic division. We're able to get rid of all those variables and exponents to get something that's easier to work with, so we don't get distracted by all the other stuff that makes it look confusing. So that's what we're trying to do here, is come up with a simpler replacement, because if I ask you to integrate u to the third du, that's pretty easy to integrate, isn't it? What's it going to become? It'll integrate the same way that x to the third dx would have. It's just now I'm going to use a u for my variable. So what would that equal? U to the fourth over 4. I mean, that's the integration, right?
How would we ever be able to reverse that? How would we ever know what that actually means?
Well, let me show you. Now that it's integrated, shouldn't I be able to go back and replace u with this? Let's see. Okay, that's what we're going to do. So instead of u, now I'll put what u equals, which is 3x squared plus 7x minus 2. That's raised to the fourth power. And I can either put the whole thing as being over 4, or if I wanted to put a times 1/4 in the front, whichever way you want to do it. Okay, and then because it came from a family, I need a plus c, right? Okay, how do we check this to know if it's been done correctly? Find the derivative. So if we were to take this function and differentiate it, so we're going to take f of x equals, I'm going to write this down again. And if I differentiate it, what do you notice we would have to use in our differentiation? Not the quotient rule, because my denominator is just a number. It doesn't have a variable in the denominator. But look here, it's a chain rule problem, because in my parentheses, I have a function with x in it. It's not just x to the fourth power. So if I were to make a chain rule table, I would have something to the fourth, and that something is the 3x squared plus 7x minus 2, right? So when I differentiate, and actually that's something to the fourth over 4, or let's do it this way, times 1/4. Okay? So now when I differentiate, what do I do with this exponent? Bring it in front, and that would become 4 times 1/4 that was already there. And then my parentheses is now going to be raised to what power? 3. And inside that parentheses is the 3x squared plus 7x minus 2. But over here, I have to differentiate what was in the parentheses. How do you differentiate 3x squared? Look at this. The 4 over 1 times 1 over 4, those cancel, don't they? And am I left with what I started with? 3x squared plus 7x minus 2 to the third power times 6x plus 7. It checks. This is how you would integrate that. Let's look at another example. Okay, so this looks like a big whopping mess. What is the first thing that you realize we should probably do? Yes, but think back even before we worry about the u. What's the first thing you see that I can't integrate if I leave it in this form? That's right. It's a radical, and so it has an index of 5. So if I were to take what's under the radical, which is the 3x to the fourth plus 8x minus 2, instead of putting it under the radical, I'm going to raise it to what power? It's a fractional exponent. The index is my denominator, so the index is a 5, and then the exponent on top is just 1, because I do not have an exponent on the parentheses. which means the exponent is really 1. Okay? So if I had the 5th root of something, that's the same thing as raising it to the 1/5 power. And then we have this 12x cubed plus 8 dx that's also multiplied by it. So that's the first thing I do. Rewrite it so you don't have a radical. Now, I think, Hannah, you said we should try U-substitution, correct? And what do you think U is going to need to equal?
The 3x to the 4th plus 8x.
Very good, because this parentheses has the larger exponent. When I compare the two parentheses, let's let U be 3x to the 4th plus 8x minus 2. Now I need to see what I get for du if I differentiate this. So 3x to the 4th becomes what? 12x to the 3rd, and then differentiate 8x and you get, and that's going to be a 0 when I differentiate -2. And because I differentiated, remember this was with respect to x. Okay, does that look like that's going to help us? Let's see.
So is it all going to be the same pattern?
Yeah, I mean, this is the process we're going to go through. If we see that we've got polynomials that are being multiplied together, we're going to have to try to figure out if one of them's u, when I find the du, will it give me everything I need in the extra stuff that's out there that's giving me the problem. So let's see if we were to think of this parentheses as u to the 1/5. I've got everything taken care of here. Do I have everything I need for the du?
Yes.
There you go. We are going to be able to replace that with u to the 1/5 du, and now I can integrate that. How do you integrate u to the 1/5?
Oh.
Okay, add 1 to the exponent and divide by the new exponent. So if I'm adding 1, that's like adding 5/5. So that would be 6/5. So that's going to be the pattern for my integration. I probably don't want to leave it as divided by 6/5 though. So can you tell me this u to the 6/5 power is going to be, instead of divided by 6/5, we'll write it as multiply by the reciprocal, which is 5/6, right? Dividing by a fraction is the same thing as multiplying by the reciprocal. This thing has been integrated, right? Okay, am I done? Do you see any u's in what we started with? No, it came to us as x's. I can't leave my answer with u's. I have to go back and replace with what we said u was going to equal. So this is going to be 5/6 times, now what do I replace u with? 3x to the 4th plus 8x minus 2 raised to the 6/5 power, and then don't forget your plus c, right? Now, we probably need a little assurance that we have done this correctly. I want you to use the chain rule, differentiate this, and see if you come up with what we started with, okay? Did it work? Okay, so if we're checking using the chain rule, we know we have 5/6 times something raised to the 6/5 power, and that something was the 3x to the 4th plus 8x minus 2. So if I differentiate, when I pull down this exponent and multiply it times the 5/6 that's there, what does that become? 6/5 times 5/6 is 1. And then my parentheses is the 3x to the 4th plus 8x minus 2 raised to the 6/5 power. Oh, no, I'm sorry. Not raised to the 6/5 power because I got to subtract 1 from it. And 6/5 minus 5/5 is 1/5. And then when I differentiate the 3x to the fourth, I get 12x cubed plus 8. And now if I go back and I check this against the original, I have all the pieces I started with, don't I? The only difference is here it's written to the 1/5 power instead of written with the radical. Okay, so give me a quick signal. Is this a thumbs up, thumbs down, somewhere in the middle? How are we doing? Okay, yeah, the more practice, typically, the better you get. So look at this one. And this one is one that I am a little apprehensive about. What do you see that's a problem if we were going to try to integrate this? Well, here's the issue. My denominator has variables in it, right? And there's more than one term. So I can't really just take the denominator, raise it to the -1 power, because then I can't really, I've got two terms on top. I can't distribute through. I've got some issues here. So I think we need to figure out if it's possible to do a U-substitution. If I were going to try to do a U-substitution, what do you think we'd let U equal? Yeah, the denominator. So let's see if that would work. If U equals 2t to the 4th plus 16t minus 1, what would that mean D would have to equal? 8t to the 3rd plus 16. Now, and of course that would be dt, okay? Do I have that? If I use this to be U,
Well, 8, you can.
Excellent, Hannah. If I were to factor out 8 and write this as 8 times, and then in parentheses, if I have t to the 3rd plus what? 2, then here's what I see. Because I can distribute back, it gives me this. But by writing it in this form, I've got this and this that I need to replace. It's just I've got something extra now in the du. And as long as what's extra has no variable with it, if it's just a constant, I can fix that. Okay, that's doable. Because remember, you can insert, like whenever we have constants, those can be pulled outside the radical, so we can work with constants because they don't affect the integration. We just have to account for them. Okay, so let me show you what this is going to look like if we start doing replacements. Before I do that, though, let me just ask, does the idea of looking at this, realizing I've got a problem like it's written, and deciding to let U equal this denominator, everybody's recognizing that's where I'm going to begin, right? And then now the only extra thing that's new is when we found the du, this had primarily what I was looking for. I could definitely see I had the variable to the right exponent, but I had to recognize to factor out this common factor so that I could see I have the 2 cubed plus 2. I have my dt. What I'm missing is I've got this extra factor of 8. So here's where we are. I have u in the denominator, and my numerator has the t cubed plus 2 dt part, but it also needs an 8, right? So what that means is I have 8 on top and the du, and I can either put the du next to the 8 in the numerator, or I can put the du at the end. But I've now accounted for all the pieces. There was my u. By putting in this 8, I've got the du covered. But here's the problem. I just now stuck an 8 in there that wasn't there to begin with. I've changed it, but it needs to mean the same thing. What could I do to counteract putting in times 8? What would undo that? Multiply by 1/8. In other words, I can multiply by 8 to get this in here as long as I also multiply by 1/8. Because 1/8 times 8 will give me 1. Does that make sense? So if I'm needing an extra constant in my du, I can work with that, because if I put that in here, I just have to remember that I'm going to pull this out here, okay? So technically, this 8 isn't here, okay, because it's part of the du. I shouldn't have written it that way when I wrote it down, because all of this is the du. It's just I needed the 8 to go with it. So when I put the du here, the 8 is included in the du. Does that make sense? And then you got to put the 1/8 in front. So this was the missing piece that as long as I added in the 1/8, I'm good. So now we're integrating where it's 1/8 and we're integrating 1/u du. I think I know how to integrate 1/u. What is it going to be? Perfect. It is the natural log of the absolute value of u. Now, am I done? Because my original problem did not come to me with u's as the variable. It came to me as x's and as the part of as what the variable was. So now I've got to replace u with what's going to go in place of u. There you go. 2t to the 4th plus 16t minus 1. All of that is in the absolute value bars plus c.
Why do we keep the 1/8?
Why do we keep the 1/8? Because when we replaced the t cubed plus 2 dt with a du, we had to have an 8 that was part of that to be a du, but in order to not change the value of the original, it meant we also had to multiply by a 1/8. So that's why this 1/8 is there, and it doesn't go away. It's got to be 1/8 times whatever we got when we integrated this.
Even when we multiply those two together equals 1, we don't take it away after that. We still keep it.
No, the reason we're putting it there is because if these two multiply together, it will give us 1, which is what we were trying to get what we originally have. Since I needed this, I can insert it as long as I also insert the factor of 1/8. And that means this gets used up in the du, but because I put this in here as part of the du, I've got to keep the 1/8 to be multiplied with it so that it really does balance it out and make it mean the same thing. Now, just to make sure we did this right, let's differentiate this, because if we differentiate and it doesn't give us what we started with, then that'll tell us we did something wrong. So this will show us if we really needed that 1/8 or not, okay? So does this look like it's probably a chain rule table for differentiating? And that is going to be very common if you're using a U-substitution. When you check with differentiation, you're probably going to be using a chain rule table most of the time. So if we started with 1/8 times the natural log of something, and that something is 2t to the 4th plus 16t minus 1, okay? When I find the derivative, 1/8 times the natural log of x would differentiate as what? Do I keep the 1/8?
Yes.
Yes, I do. And then how do you differentiate the natural log of x? It becomes 1/x. Now the x is this whatever's inside the absolute value bars, and that's the 2t to the 4th plus 16t minus 1, right? Okay. Times, now we got to differentiate the 2t to the 4th and get 8t cubed plus 16. And that would be over 1 if I want to think of it as fraction times fraction times fraction. Now, That doesn't look exactly like what I started with, but what do you notice we might be able to do to kind of clean things up a bit? The 8t to the third plus 16 can be factored into 8 times t cubed plus 2. And now, if there's an 8 on top and an 8 on bottom, what happens to those 8s? They would cancel out, and I would be left with the t cubed plus 2 on top over the 2t to the fourth plus 16t minus 1 on bottom, which is what I started with. That's how I know this is the right answer. If we didn't have that 1/8 there, then we couldn't have gotten the right numerator. Does that make sense?
Yeah.
It is a lot to take in, okay? And the good news is this is honestly what we have to do after this, you're going to think is really simple because all we're going to do is evaluate. And it just means when we finish our integration, we'll be able to calculate what an actual area is. If you remember the other day where I gave you the illustration of this lets us add up all those little rectangles under the curve, the only thing left to do now is to tell you, maybe I want you to add them all up from x equals 0 to x equals 3. And I'll show you how to do that, and it's very simple. That part's not going to be hard. This is the last of the kind of have to put your thinking cap on type of stuff. All right, look at 4. This looks easier to me than some of the other things we've looked at. Is there any reason we need a U-substitution here? There you go. The problem is it's not just e to the x, it's e raised to a power that is something that has x in it. That's my clue. I need a U-substitution. So what do you think u should equal? There you go. That exponent. Negative 0.9x. Now, if I differentiate that, what do I get? Negative 0.9, and then that is with respect to x, right? So negative 0.9 dx. That shows we differentiated it. So if I get ready to do a u substitution, I have all of this that would be my u. Do I have everything I need for the du? What is included in du that I don't have up here? The negative 0.9, correct? That's in my du, but it's not up here with the dx. I've got the dx, but I don't have this as a coefficient, right? Okay, is that fixable? It is because it's just a constant. Yeah, so let's see if you can tell me how you might want to rewrite this. We would be integrating e to the u. Now, in order to put du here, what am I going to have to do? There you go. Since this has to be included as part of the du, I also have to multiply by the reciprocal of this. So what Sarah was saying is we could think of it as negative 1 over 0.9. Okay, which is kind of a funny way to write it. I mean, think about 0.9 as being 9/10. We could have written it as negative 10 over 9, and that's the same thing as negative 1 over 0.9. That makes sense? And we'll clean this up in just a minute. But if I do my replacements this way, am I good now? I think so. This is ready to integrate. And how do you integrate e to the u? It's just e to the u. So double check. Let me just show you. If I were to take negative 1 and I were to divide that by 0.9, that's what it looks like. If I turn it back into fraction form, it's a negative 10 over 9. So if it's okay with you, instead of leaving it this way, I'm going to write it as negative 10 over 9. And you said e to the u integrates as e to the u. But I don't think I want to leave it with the u because it came to me with x's. So what would you say this should equal negative 10 over 9 e to the what? And it's got to be a negative 0.9x, right? Plus c.
That plus D is going to
Yeah,
be
it's
me.
gonna be. Every time I was typing it into the homework, I kept getting.
I know, and that's what's going to happen on the next section when it's definite, and we're going to be integrating, say, from x equals 0 to x equals 3. There won't be a plus c anymore because we're actually going to get what the area is. What we're doing is explaining that this family of functions would all have differentiated to give us this. So that's why the plus c is there, because we're not working with the area. We're just talking about what kind of function would you have differentiated to get this. Now, do you think we need to double check this to make sure that this is actually integrated correctly, or do you get the idea on the check how to do that? Do you feel like this was simple enough? We're good.
Get the idea of the check.
Okay, so if you got the idea of the check, we'll skip that one and let's look at the next one. All right. What do you think needs to happen here? Actually, let me tell you what needs to happen here. We're going to skip these, okay? These two are a little bit goofy. We're not going to have questions like these, but we're going to go to, I know, yeah. So let's go to number 7. This one, I do think we need to look at. It's okay. It's all right. Yeah. It does look a little funky, but I want you to think through, does this look like I probably need a U-substitution? And what do you think U should equal?
The
I think Angela is on to something, because think about this exponent. You've got negative 1 over x to the 5th. X to the 5th is on bottom here. X to the 6th is on bottom here. Remember we said let U equal which one? And because these are on bottom, isn't x to the 5th in the denominator actually larger than x to the 6th in the denominator? That's a little goofy as far as the way that it's set up. But you're exactly right. Negative 1 over x to the 5th is what our u should be. Now, in order to find the du, I think I probably ought to rewrite this. I don't think I want to try to differentiate it with that x to the 5th in the denominator. So that's the same thing as what if I write it with where there's not a fraction. Negative 1 times x to the negative 5. Okay, now let's differentiate that. What's that going to give me? Okay, the negative 1 that's here times the negative 5 in the exponent becomes a positive 5. And then, yes, because I'm subtracting 1, that's x to the negative 6. Or it would be 5 over x to the 6th. And remember, we differentiated, so that's with respect to x. Now, let's kind of we'll take inventory and see if we've got all the pieces we need. This is going to be what? That's our u. Now, for the du, I need a 5 over x to the 6th dx. I've got the dx. I've got 1 over x to the 6th. So the only thing I'm missing is the 5. Can I fix that? Well, this is 5 over 1. So if I'm thinking about, I'm actually sticking in a 5 over 1 in order to turn it into a du, then I have to multiply by what to counteract that? 1 over 5. So this would tell me, okay, I'm going to make a little note over here that I need to remember. I've got to multiply by a factor of 1/5. This means I'm ready to integrate if I have 1/5 on the outside. That takes care of all of my du stuff now. And I would have e to the u du. So far, so good? How do you integrate e to the u? It's e to the u. So I'm going to have 1/5 e to the u, but then I need to do what? replace u with, well, whatever u is equal to, which is -1 over x to the 5th. And then I need the plus c, right? Okay, now this one, I think we need to differentiate to make sure we actually did it right. Does this look like it probably needs a chain rule?
Looks crazy.
Yeah.
I think it needs a chain rule, okay? And here's why I think it needs a chain rule. It's 1/5 e to the something. Are you picking up on the idea that when we use the chain rule, whatever the something is really the same thing as a u? We just put an open parentheses when we use chain rule. All we're doing now is saying, okay, let's let this be u, instead of putting like open parentheses. So it's 1/5 e to the something, and that something is a -1 over x to the 5th, which we said could be written as -x to the -5. Because we did that up there. All right, let's differentiate. I get 1/5 e to the something, because I know when I differentiate e to the something, it's just e to the something. And that something was -1 over x to the 5th, dot, now differentiate -x to the -5.
5x to the -6.
5x to the -6, which is the same thing as 5 over x to the 6th. And what happens if you have a 5 on top and a 5 on bottom? They cancel. And that leaves me with 1 over x to the 6th times e to the -1 over x to the 5th. And isn't that what we started with? So it checked. Okay, so you guys have been helping me figure this out. You told me this was u. You told me this would be du. And what we're discussing now is if we have more up here than what we need, we could factor the 12x squared into 2 times 6x squared. And because this was written as dy over dx, technically, couldn't I multiply both sides by dx to get it back into a form we've kind of been used to, where this is explaining that the derivative with respect to y is all of this. And now you're telling me that part's the u. If this gets replaced this way, then I have all of this that I need for what? The 6x squared dx is my du. I just have an extra factor of 2 up here. Is that okay? Yeah, I don't get rid of it. I don't have to do anything else to it. I just keep it. Does that make sense? If the extra part's in the du, then yes, we're going to have to insert something, and then we've got to insert a factor of the reciprocal so it doesn't change the original meaning. But if I actually have more than what I need up here, and the only extra part is a coefficient or a scalar, I just need to factor that part out and I'll keep it. So we're trying to integrate. Now tell me what you would write down. So no, you're in good shape. Okay, you said we've got this u to the 5th, right? Okay, and then what else do we have? The 2, and then the du, right? Isn't that what we're going to integrate? 2u to the 5th du. Yes, ma'am. I can put it either place. You guys want to kick the 2 out?
So like it doesn't matter.
Doesn't matter, because it's not going to affect any of the integration. So if you want to put it on the outside so it doesn't look as confusing to you, stick it on the outside. If you want to leave it inside, you can. It's up to you. Now, what would you write down next?
Okay, the X.
Have I integrated? Oh, I think I need to do that. Okay, now be careful, you're differentiating. Remember, this is like pat your head, rub your belly. You gotta remember which way you're going. So, do I keep the 2? And then this integrates as what? Over 6, very good. Now, what do you notice we can do? Anything? Okay, we could reduce the 2 over 6. That becomes a 1. This becomes a 3. So I've got u to the 6th over 3 plus c, but am I done? All right, now I need to go back and replace u with what u was in terms of x. And that's going to be 2x to the 3rd plus 7 raised to the 6th power over, what's in my denominator? 3, and then a plus c. All right, your turn to differentiate. I want you to see if you can differentiate that and come up with what the original. Okay, so when you're looking at this is how you set it up in your chain rule box. To double check it, I just put 1/3 as a factor instead of writing it as a fraction over 3. So if I differentiate this, when I pull down the 6, it becomes 2. 6 times 1/3 is 2. And then in parentheses, I have my 2x to the 3rd plus 7. And what's my new exponent when I differentiate? 5. And then how do you differentiate 2x cubed plus 7? And remember, these are all being multiplied together. If I multiply 2 times 6x squared, that turns into what? 12x squared times this to the 5th power. It works. Okay, so those are your examples